Alright, in the previous video we showed that when we have a binary outcome and when we are trying to estimate odds ratio, then the change in estimate method sometimes do not provide us a good guidance on whether we have a confounder or we have something else. Basically we showed by an example that when we are dealing with a risk factor for the outcome, it can the change in estimate method can sometimes mistakenly identify that variable as a confounder based on the change in estimator method. So based on that, I wanted to explain what a phenomenon called collapsibility is, and to show what an collapsibility is, I am going to use three different type of measure of association. What is risk ratio, risk difference, and odds ratio, and I'm going to also touch a bit on conditional and marginal estimates. And in this example, to simplify, I am considering the scenario where there is no confounding at all. So similar to before, I'm using the sim causal package, and I could not use 1 million observation because of some non-convergence, so I'm just using 100,000 observations here to show the process and the data generation. So in here, similar to before, I have some examples such as hypertension is our outcome and we have smoking as our exposure variable, right? And then we have two other variables, gender and age, but these variables are basically risk factor for the outcome hypertension. It has nothing to do with smoking in our example here. Alright, so we generate the data, and hypertension is a binary variable, smoking is a binary variable, age is a continuous variable, and gender is again a binary variable in this particular example. Alright, so we do some balance checking, and we stratify based on smoking, and we want to check the balance of gender and age, and we can see that both of these variables are somewhat well balanced. Alright, so we go to estimate the treatment effect estimate, where our treatment here is the smoking and we are adjusting for gender and age. Notice that gender and age, both of these variables are risk factor for the outcome. It has nothing to do with smoking in our example, so this age and gender should not be confounders, right? So we are basically trying to estimate the risk difference here, and to estimate the risk difference, what we are doing is we are using the GLM function with Gaussian family and identity link. If you want to know why we are using this, there is a Naimi and Whitcomb paper that was published in American Journal of Epidemiology that gives some guidance of how to estimate the risk difference based on the generalized linear model function, or the GLM function in R. And we are also using the robust version of the variance estimator so that we get the correct standard error. Alright, so here look at what we are doing here. This is the outcome variable, hypertension, and this is the exposure variable, and we are still adjusting for two other covariates that are risk factor for the outcome. These are not confounders. Alright, so we can see the coefficient or the risk difference is 0.06, and we can try to check based on these two variables, gender and age, in 4 different stratum, what are the risk differences. So the way we are defining the stratums is based on whether gender equal to 1 and age is less than some particular value 2. We are choosing value 2 because when we generated the data we have chosen mean equal to 2, for the age variable, and that is how we are stratifying the data. So we are saying that if gender is 1 and age is less than 2, this is basically a standard centered age, let's say, and we are getting the coefficients which are 0.11, 0.1, 0.10, 0.01, and this is rounded to 0 basically. So when we calculate the unweighted mean, we get unweighted mean of 0.05, which is similar to what we got when we use the regression method, right? And then let us take a look at what is happening when we are adjusting for just one variable instead of two variables. So we are basically adjusting for just gender variable. We are not adjusting for the age variable anymore, and we get the similar coefficient or risk difference of 0.05, and we do the same for all of the stratas that are defined by the gender. So this is gender 1 and this is gender 0, and we see the odds ratios are very the risk differences are very similar, 0.06 and 0.05, and when we take the unweighted mean, we get 0.05, which is close to what we got from our regression model, right? And then we considered the crude estimation of association between hypertension and smoking without adjustment of any other covariates, and we again get the risk difference of 0.05. So in this example, what I'm trying to show is that when the variable age and gender are not confounders, the coefficients or the risk difference that we are getting out of all of these methods, when we are adjusting for nothing, when we are adjusting for just one variable, or when we are adjusting for let's say two variables, it does not matter. We are always going to get very similar estimate. The risk difference is very similar. It's varying between 0.05 or 0.06, which is again very close, right? So this is risk difference. We can do exactly the same thing when we are estimating the risk ratio. And basically what we can do in terms of estimating the risk ratio from a generalized linear model is that we can use the Poisson family with the log link, and we can use the robust estimation of the standard error so that we get the correct standard error. And in terms of risk ratio, we get 1.08. In terms of the stratum specific, there are some specific stratum specific estimate that we get, and when we take the mean of them, we get 1.15 or 1.16, which is not that far from 1.08 that we got out of the regression model, the Poisson regression model. And then we can do the same for adjusting for only one variable instead of age and gender. We are just adjusting for gender. We can get the risk ratio of 1.08, and we again can do the stratum specific version, and we can get the mean of them, which is very close to 1.08. And when we estimate the crude risk ratio, and we are not adjusting for any covariates, we get the risk ratio of 1.08. So what is happening in both risk ratio and risk difference is that when age and gender variables are not confounders, these are basically risk factor for the outcome. Irrespective of whether we are adjusting for one of them, both of them, or none, we are essentially getting very similar estimates in terms of risk difference as well as risk ratio. In terms of risk difference, in all of these variable adjustment combinations, we are getting 0.05 or 0.06, very close, and in terms of risk ratio, we are always getting 1.08, right? So both of these are known as collapsible estimates. What that means is that when you are adjusting for something and not adjusting for something, it does not necessarily matter. The conditional estimates that you are getting when you are adjusting for two variables that are not confounders, and then when you are adjusting for just one variable that is not again a confounder, and when you are not adjusting for any covariates that are not confounders, you are essentially getting same results all the time, and that will happen not only in risk ratio, that will also happen in risk difference. Or you can say the other definition, where if you have some stratum specific values, the stratum specific values would not be different than the original combined value that you get by combining both of these stratum into one estimate. So you are basically not adjusting for any of these gender variable here, and when you even adjusted for them in the regression or in the stratified analysis, you are essentially getting very similar results. This is the phenomenon that we call as collapsibility. All right, now let us take a look at what is happening in terms of the odds ratio. So in terms of odds ratio, what we are basically doing in terms of family, we are just assigning binomial with logit link, and we are again using the GLM function. There are some issues with this GLM fitting, but that doesn't necessarily matter too much. But in here what we are getting is that our odds ratio is 3.37 when we are adjusting for both age and gender, right? And then we are trying to estimate the stratum specific values again, and we can see instead of getting values close to 3.37, we are getting wildly different numbers. In just one case we are getting very similar to 3.37, and when we take a mean of all of these stratum specific odds ratios, we get 2.18, which is not close. And when we are again not adjusting for age variable, we are getting a very different odds ratio of 1.229. But then again, when we do the stratum specific adjustment of like when we are just adjusting based on the whether it is gender equal to 1 or gender equal to 0, we are getting odds ratio very close, 1.29, which is very close to the regression estimates that we got. And we can try to combine this estimate instead of doing this unweighted mean. We can try to use the Mantel-Hansel estimate of the adjusted odds ratios, and we can get the odds ratio of 1.29. And then when we do the crude analysis, we again get the odds ratio of 1.29. So according to the definition of collapsibility, the definition says if you have a unadjusted odds ratio, and then if you have a adjusted odds ratio, and this adjustment could happen in terms of the stratum or it can happen in terms of the regression, but irrespective of how you do the adjustment, you always get the same estimate when it is conditional on adjusting for gender. Here we get an odds ratio of 1.29, and in here we didn't adjust for anything and we still got the odds ratio of 1.29, right? So in this particular example, in this last example, this odds ratio is collapsible, but when we adjusted for two variables instead of one variable, so we adjusted for gender and age, then we got an odds ratio of 3.37. So that means that this in this particular scenario, odds ratio is not collapsible, because when we adjusted and when we didn't adjust for, say for example, this age variable, the odds ratio estimates were very different, right? Okay, so this is an example where odds ratio is non-collapsible, and this is an example where odds ratio is collapsible. So even though this is a conditional estimate and this is a marginal estimate, both of these are giving us very similar odds ratio. So in this case, when we are just adjusting for gender, we get a collapsible odds ratio, whereas when we adjust for additionally age, and that is an example of non-collapsible estimate. All right, so Then we can try to estimate marginal version of risk difference, risk ratio, and odds ratio. And in terms of how we estimate this marginal estimates, there are a bunch of references that I can put you below, but basically what we are doing here, this is very similar to the G-estimation method, where you have a regression where you have hypertension as the outcome and you have smoking, gender, and age variable, and then you feed the regression, and this regression is, say for example, fit x3 is our logistic regression fit. And then what we do is that in the original data we assign all of the person to be a smoker, and then we try to predict based on this regression what is the predicted value when everybody was a smoker. And then we also do the same, but this time we assign everybody to be a non-smoker, so we try to predict what would happen to the predicted probability of hypertension if everybody was a non-smoker, right? So we are basically changing the assignment of the treatment variable only. And when we do that, and we get the mean of the predicted values from both of this scenario where everybody was a smoker versus nobody was a smoker, we get the probability of getting hypertension where everybody was a smoker, and this is denoted by P1, and we get the probability of the risk of hypertension when nobody was a smoker, and this is denoted by P0. Once we get these probabilities, we can easily estimate the marginal risk difference, marginal risk ratio, and marginal odds ratio, right? And we can also try to estimate based on this fit x3, because this is a logistic regression. Basically, we can try to estimate the odds ratio in a conditional way. So the conditional odds ratio is basically the exponentiation of this beta coefficient associated with this smoking variable, right? So that would give us a conditional odds ratio, and there are some other methods to estimate the risk ratio and stuff like that. I'm not going to go into details of that. But what we are getting here is that when we are adjusting for two variables, we are getting the marginal risk difference of 0.05, marginal risk ratio of 1.08, and marginal odds ratio of 1.29, whereas the conditional odds ratio was 3.37, which was different than the marginal estimate. But if you remember, like when we estimated the conditional risk ratio based on the Poisson regression, we got 1.08 as well, and when we estimated the risk difference based on the Gaussian family identity link, we also got the conditional risk difference of 0.05. So conditional and marginal risk difference and risk ratios were very similar, but conditional odds ratio versus conditional the marginal odds ratio, they are very different, right? And this is happening when we adjusted for two variables. Let us see what happens when we adjust for just one variable, gender, and then we can see very similar result in terms of the marginal risk difference, risk ratio. Even marginal odds ratio is exactly the same as before when we adjusted for two variables. The only difference is that now we get conditional odds ratio, which comes down to 1.29, which is now similar to the marginal. So marginal and conditional are exactly the same when we just adjust for the gender variable. This was the same scenario where we have seen in the previously when we were estimating the odds ratio and we adjusted for just gender variable, we got similar estimate with or without adjustment of gender variable, right? So you can simplify the definition of collapsibility in the sense that whether your marginal and conditional estimates are similar or not. So in this example, your odds ratio, marginal and conditional, are similar. So in this example, when you are adjusting for gender, you are getting a collapsible estimate, whereas when you adjusted for just two variables instead of gender variable, you adjusted for gender and age variable, then you get the marginal and conditional estimates that are very different. And that is why in this example, when you adjusted for two variables, you did not get a collapsible odds ratio in here estimate. And then when we didn't do any adjustment, you can see again these values are exactly the same as these values when we just adjusted for the gender variable, right? And you can go back to some of these references that talks about the marginal standardization and standardized versus population averaged versions. And Peter Austin basically called this clinically meaningful measure of treatment effect when we are getting our estimates from basically a logistic regression, right? So just to summarize, when we take a look at all of these strategies that we have taken under the conditional estimate and versus when we estimated based on the marginal methods, we can see the risk differences basically remain the same, very close to 0.05. The risk ratio basically remained the same, except for this scenario when we stratified based on these four groups. This is slightly different, but in all the other cases, even the conditional and marginal were very similar, 1.08. The difference is in the odds ratios. When you compare the odds ratio with two variable adjustment versus one variable adjustment, you can see there are sometimes you can see difference and sometimes there are no difference. When you just adjust for gender variable versus no adjustment, you basically get the same estimate. And in terms of the estimates of risk difference, risk ratio and odds ratio, we always got very similar estimates for any variable combinations, right? So we can simplify the definition of non-collapsibility as whether the marginal and conditional estimates are different or not. So in this example, say for example, even though this is a conditional estimate when we are adjusting for gender and when we are not adjusting for anything, this is an example where odds ratio can be collapsible. But this is an example where when we are adjusting for both age and gender, odds ratio is not collapsible to either this estimate or this estimate, right? So and you can take a look at some of these references that I'm listing here, and to summarize what a collapsibility is, if you have a regression of an outcome and then you are trying to predict that outcome based on a treatment and a separate variable which is not a treatment variable, and then you are having a second regression where you have just the treatment variable to predict your outcome. If this beta estimate from the first regression is similar to the beta prime estimate from the second regression, we basically call the estimate to be collapsible, right? Or the other definition could be when your marginal and conditional estimates are similar, you can also call that to be a collapsible estimate. But sometime, because of the fact that odds ratio is coming from a nonlinear transformation in the logistic regression, sometime the collapsibility might not be present in the odds ratio, but collapsibility is generally present in the risk ratio and risk differences, at least in the examples that we have shown earlier.